Well, hello. So in my independent variable video, I talked about a MOKE experiment and I had some diagrams and stuff. So here I'm just going to show really what happens in a real system. So here we have our MOKE. Now we have several components here. So if I put the phone in there, you'll see that there's a little white light there, and that is the on indicator of a laser, which is the black box, slightly left to it. Now we have a laser that is passed through loads of optics to make sure that the beams are nice and parallel. But here we have the laser coming through on this mirror here, and then it passes through this polarizer. Now the laser that is passed through this polarizer is polarized upwards, and then it goes through the lens and it hits a sample which is just mounted there, which is that glass slide. Now the laser is then reflected off that sample and it passes through these lenses here all the way through, and then it is then bounced to this detector. But here we have another polarizer which is orientated orthogonally to the first polarizer, so it only allows light through that is polarized left to right. Now here we see these big electromagnets, and when I turn these on, it will pass a sinusoidal magnetic field. So it starts off pointing in that direction, then it increases and decreases again and starts pointing in that direction. Now what this does is, because this sample has magnetic material on it, that changes the magnetization of that sample. And there's something called the magneto-optical Kerr effect, which means that the polarization of the light is changed depending on the magnetization of the sample. And because in a reference state, this polarizer polarizes the light up, and this polarizes across. So in a reference state, what happens is that we configure it so there is zero signal passing through this polarizer. But when the magnetization changes, then that signal becomes non-zero because it rotates slightly, and that gets picked up by this detector. I've now turned off the lights to show you some of the challenging components of this. Now, if I just move this filter, you'll see that there is a laser hitting the sample. Now this bit here is a camera, and it allows us to see what's happening on the screen. And we see this size laser spot. Now the laser spot is actually around 5 or 10 microns in size. But if I put the filter back, you'll be able to see the problem. So what we are trying to do is align them to one of these structures, and this is one of the structures we align, and we can see here that the resolution of our camera is actually too large to resolve this wire, and this wire is about 200 nanometers wide, and we're trying to align this. But once we have the alignment, we can turn the experiment on and we'll hopefully get some results. What I'll do now is I will take this flashlight out of the way, as I no longer need it. And then I put a lid over the top. Now we've had to cut a hole in the lid to facilitate this thing, and take the other lid, because all the light, even how dim it is, can really interfere with this experiment. And then we cover it up so the air conditioning doesn't interfere with it either. There we go. Now here we have some equipment. So what we have here is a power generator. This applies, this sends a current through that big electromagnet. And then here we have the readout of a Gauss meter, which sits between the magnets, and that measures the magnetic field. Now if we go back to our computer, we have this view here, and when we turn this on, we see fun stuff happening. So the key bit here is this graph whereas on the x-axis we have a measurement for the magnetic field. And here, on the y-axis, we have the amount of light being passed through the second polarizer. And hopefully we will start seeing some interesting patterns coming up soon. But this will take a while. As you can see, that this signal is very noisy. So what we need to do is run this for a very long time, because then the noise starts cancelling itself out, and then we may find a signal in there. So after 182 repeats, we see this result, and this is not telling us anything. This means that either there is no magnetic material on my sample, or the more likely result is that the system is misaligned because I have seen the magnetic material on the sample. After realignment, now I've started running again. We're at 185 loops so far. And we do see that there is a region here where the signal seems to be higher, then we have a drop off, and then there's a flat signal again at a lower stage. Now, at the moment, this could still very much be pareidolia, and we can't really say that this is a significant result. However, this drop here is something that we do expect. So we now need to run it for another 800 loops or so, and then we will start being able to see if the signal is there. And if we then decide that the signal is there, we will run it for another 19,000 loops or something like that, and just keep continuously running it, and then we get better signal to noise ratios. And the longer we keep things running, the more certain we can be that what we're seeing is actually there. Okay, so it has been running for a couple of hours now, so let's have a look. Okay, so we are 5,000 loops in, nearly 1,100, and you can see that out of all of that noise, we've now got some really nice signal. And this can give us lots of information about it. Now, it is still far from perfect, so I'm going to run it for another 15,000 loops. Perhaps I may even run it overnight and come back tomorrow to see actually what comes out. Now, what you see here are called hysteresis loops, and the structures we're measuring are small wires, like the one shown on the screen here. And what we see in the wires, we have all these arrows which represent the direction of the magnetization, or each magnetic spin in the wire. As you can see, they're all aligned, lying along the long axis of the wire. But when we start applying a magnetic field in the opposite direction, they start getting a bit perturbed. And once the magnetic field in the opposite direction is strong enough, what happens is that you see two structures on each end of the wire nucleate, and they're called magnetic domain walls. And they move towards the center, and they meet in the center to annihilate. Now, what you then see is that the magnetization of the wire has reversed. And for it to be reversed back again, it needs to apply a magnetic field in the opposite direction, which is also needs to be significantly large. And what you then get is a characteristic hysteresis loop, as the one I will show on screen. That's it from me for now. This is really an outline of what MOKE looks like. I will be doing a lecture on tiny magnets at the end of next month, and this is going to be aimed at 17 to 18 year olds, which will be quite entry level for a lot of you. So this will be recorded, and if I can secure the rights to that, I will upload that and make that a Patreon only video. Alright, until next time.